Assalamualaikum and good morning everyone. I know all of you still in Hari Raya mode, so selamat Hari Raya. I believe all of you enjoy celebrate Hari Raya with your family and your friends. Okay, but don't forget class still on. Okay, from the previous lecture, we have covered the introduction of quantum theory, okay, about the nature of light. Today we will learn about atomic spectra. Okay, what is black body radiation? Okay, black body radiation phenomena happen when a solid object is heated, okay, to about 1000 Kelvin, and it will emit visible light. That's what we call black body radiation. Okay, and the color and the intensity of the light depend on the temperature. Okay, it will change as the temperature change. Okay, and the color also relate with wavelength and frequency, while temperature relate with energy. Okay, so the relationship between energy, frequency, and wavelength will derive these equations, where E equal to energy and H equal to Planck constant. As you can see from this figure, these are examples of light emission related to black body radiation, such as smoldering coal, electric heating element, and light bulb filament. Okay, based on quantum theory of energy, it states that any object, including atoms, can emit or absorb only certain quantities of energy. Okay, since energy is quantized, meaning that it only occurs in fixed quantities, so this is called quantum. Okay, so that's what we call the quantum theory of energy. Okay, atom change its energy by emit or absorb one or more quanta of energy, and from this theory it derives this equation. Okay, photoelectric effects provide evidence for the existence of the photon and the particle-like behavior of electromagnetic radiation. As we can see from this figure, we can see that the light strikes the metal surface, is the metal surface, and it will produce the free electrons, and the free electron travel to the electrode and produce current. Okay, sample problem 7.2 show us how we relate the energy, wavelength, and frequency. Okay, so from this problem, we need to determine the energy of one photon of the microwave radiation, given the wavelength of the radiation is 1.20 cm. So we need to find the energy. Okay, so we know that energy equal to hv. Okay, so we need to given the wavelength of the radiation, which is 1.20. Okay, so we know that E equal to hv and V equal to C over lambda. So we are given the lambda here. Okay, so we know the Planck constant. Okay, so we also know the c, speed of light. Okay, so we substitute the value into these equations. Okay, but please make sure we need to convert the unit of cm into a meter, so that it will the same with the unit of the speed of light, meter. Okay, then we solve these equations, then we get the value of energy for the one photon of microwave radiation. I believe all of you know the famous story of Isaac Newton. Okay, he put a narrow beam of light through a prism, and the prism separate the white light into different colors of rainbow. And all these colors we call continuous spectrum, like you see here. Okay, this is what we call continuous spectrum. There is no gap between the spectrum, and you can see the continuous spectrum from red to violet. Okay, and all these colors is continuous because you see these colors next to each other. However, if you did the similar things with hydrogen, you don't see a continuous spectrum. Okay, for example, if you pass a current through a tube containing hydrogen like this, okay, you can find that the electrons in the hydrogen atoms are going to absorb energy and jump into higher energy. When those electrons fall down to a lower energy level, they emit light. If you use something to separate the light, like prism, like this, okay, for hydrogen, you don't get a continuous spectrum like this, okay, but you for hydrogen, okay, you will see these four lines of colors. Okay, you will see these it will give you four lines of colors, which is red, light blue, blue, and violet. Okay, so since you see lines, okay, so since you see lines like this, okay, so we call this line spectrum. Okay, these are the line spectrum for hydrogen. Okay, as we can see, the red light, okay, the red line, okay, has a wavelength at 656 nanometer, and the green blue has wavelength at 486 nanometer. The blue one has wavelength at 434 nanometer, and the violet has wavelength at 410 nanometer. Okay, so we so this emission spectrum is unique to hydrogen. So this is one way to identify the element. So since line spectrum are unique, this can explain where those wavelengths come from. Okay, so since line spectrum are unique, we can use Ribot formula to calculate the wavelength of spectral line in many chemical elements. Okay, we can use Ribot equation, and we can see that 1 over lambda, okay, you can see that lambda is wavelength of the light that's emitted. Okay, R is the Ribot constant, and N1 is equal to lower energy level, and N2 is the higher energy level. Okay, you use this equation and you can get the wavelength of the light that's emitted. Okay, according to Bohr atomic models, it states that each atom has only certain energy level that we call stationary state. Okay, each state is associated with fixed circular orbit of electron around the nucleus. The higher the energy level, the farther the orbit is from the nucleus. Okay, when the H electron in the first orbit, it is in lowest energy state and we call it is the ground state. Okay, based on the theory, it states that the atom change to another stationary state only by absorb or emit a photon, and the difference between the energy of two energy states we call the energy of the photon. When the electron in orbit higher than n equal to 1, we call the atom is in excited state. Okay, as we can see from this figure, we can see that the atom change to another state by absorb or emit a photon. We call here absorption and emission. And the difference between the two energy states we call the energy of the photon. When the electron in orbit higher than n equal to 1, okay, we call it is in excited state. However, when it is in lowest energy state, we call it is ground state. Okay, as we can see from this figure, we can see that each state is associated with a fixed circular orbit of the electron around the nucleus. We can see that the higher the energy level, the farther the orbit is from the nucleus. And we can see that when H electron in the first orbit, okay, n equal to 1, okay, we call it is in a ground state. Okay, we also, from this figure, we also can see that each spectral series has a different value of n1. For example, infrared series, it has n1 equal to 3, visible series has n1 equal to 2, and ultraviolet series has n1 equal to 1. Okay, so based on the theory, it states that, okay, the when the n when the n equal to bigger than 1 and 1 is bigger than 1, so it is in excited state. Okay, so you can see that the energy of attraction is greater when the electron is closer, meaning that the atom release more energy, okay, since the wavelength of photon is shorter when the electron move from n to n1 compared to when it moves from n3 to n2. Okay, this is the analogy for defining the energy of a system. Okay, like uh, this chemistry book, when it's put on the table, it's potential energy, and when it moves, when it falls down, it is converted into kinetic energy. Okay, so the difference between the energy, okay, we can use this formula to get the difference between the uh, energy. Okay, let's see sample problem 7.3. Okay, based on this problem, we need to find the change in energy of the atom and the wavelength of the photon. Okay, based on this problem, it states that the hydrogen atom absorbs a photon of UV light and its electron enters the n equal to 4 energy level. Okay, as we can see that when it absorbs a photon of UV light, meaning that n equal to and 1 equal to 1. Okay, you can refer figure 7.11. Okay, so then we need to find the change in energy and wavelength of the photon. Okay, based on the problem, you can use this formula to find the change in energy of the atom, and then substitute the value into the equations, then you can get this value. Next, you need to find out the wavelength of the photon, right? So you can use these equations and substitute the value into this equation, and you can get this value, the wavelength of the photon. Okay, as we can see from this figure, you can see that the fireworks display emission similar to those seen in flame test. Okay, why the flame produce color? This is due to the emission of light of a particular wavelength by each element. As we know that when the atoms um, absorb energy and jump into higher energy, and the electron fall down to a lower energy, they will emit a light. This is why the flame produce color. Okay, actually, type of spectrum given off depends on the objects involved. For your information, there are three types of spectra, which are continuous spectra that we have learned from the previous slide, emission spectra and absorption spectra. As we can see from this figure, what's the difference between emission spectrum and absorption spectrum? We can see that the emission spectrum, okay, we can see that a series of line spectrum, okay, against a dark background, while for absorption spectrum we can see that a series of dark spectral lines among the colors of the rainbow. Okay, so these are the difference between the emission spectrum and absorption spectrum. Okay, these are the example of the application of UV visible light, and from this figure we can see that the source emits many wavelengths. Okay, and then what happened? Okay, the uh, the the light, okay, will disperse into the will pass through the prism, and it will disperse into into its component of wavelength. And what happened, you put your sample here, and the sample only absorb a characteristic amount of incoming wavelength, and here is the detector, where the detector can convert the radiation into electrical signal. And here, okay, you can see your data in the computer. Okay, let's say you want to measure the chlorophyll in leaf extract using UV spectrometer. So you know that the wavelength, the sample absorb the wavelength at this range, okay, at this wavelength. So using the UV spectrometer, you can get this peak at wavelength 663 nm. Okay, you can refer journal. Okay, then you can get the absorbance value for the sample. Okay, but in order for you to know the unknown concentration of your leaf, first you need to make calibration curve. Okay, so you need to make a calibration curve first. Okay, you need to prepare your standard, and you need to prepare standard where you know the chlorophyll concentration. Then you can get this graph. Okay, make sure R equal to 0.9 above. Okay, but the best is 0.99, approach to 1. Okay, in order for us to find the unknown concentration of chlorophyll in the leaf, okay, we already plot the graph, okay, with the standard chlorophyll concentration. Then, in order for us to know the unknown value for the sample, okay, we can know from this calibration graph. So let's say you run your UV using this leaf, your sample, and you get this peak. Okay, you get the wavelength, okay, and you get the value for absorbance. Okay, so in order for you to know the concentration of unknown, you already know the absorbance at 663 nm, so you can know from this plot. Okay, so then you can get the chlorophyll concentration for leaf extract.